In this video, we're going to look at the properties of integrals, specifically without looking at the concept of the area under the curve, and just simply looking at the integral and the properties that the formulas will allow us to see. So our first property right here is the integral from a to a of f of x dx. Now if we recall, again, the integral of this is simply just the area under the curve of f of x from the value of a to the value of a. Well, if the distance between these 2 points, the start and the end, is 0, well then the integral will end up being 0. So the integral from any number to the same number of any function is equal to 0. The second property here tells us that if I have some kind of constant multiplied by a function, just like with the summations, that constant can be pulled out of the integral. And again, these bounds are not important in terms of what they are. It's just a matter of if there's a constant inside the function multiplied by that function, that constant can be pulled out. Next, if you'll notice, as x goes to from a to b of f of x dx, it is equal to the negative of the integral from x equals b to a. So again, if you think about the areas, this is simply the concept of the integral from a to b is equal to the negative area if we're calculating that area backwards. And again, that's the concept, is that instead of calculating it from left to right, we're calculating it from right to left, or vice versa, and again, it negates the value of that integral. This one here simply allows us to look at, again, multiple different pieces all combined together. So if I've got an area under the curve of f of x from a to b, then this is the same thing as the area under the curve from a to c, then adding to that the area from c to b, assuming that c has to sit somewhere between a and b. With these four properties, these four rules, we can go ahead, without given any graph whatsoever, simply be given 3 different integral forms and understand how to utilize them. So if we look at these, the analysis of this is that as I go from 0 to 5, the area under the curve of f of x is 9. However, from 2 to 5, so if you think about it again, there's a distance from 0 to 5, and then a distance from 2 to 5. This overall distance here, the area under the curve of that space, so again, there's some curve being graphed here, the area under that curve is 9. However, the area over here is simply 4. Okay. We also have one other detail given, and that's x equals negative 1 to 5 of f of x. And again, these should both have dx's in them. Let me adjust that right now. So that means that somewhere sitting back here, that entire space, being entirely covered, is going to be a value of 3. Okay. So this should provide us with some kind of analysis of what we're going to need to look at for the rest of this. But let's look at detail by detail. The first one, the integral from 1 to 1 of f of x dx, no matter what the function, again, no matter what the function, will always be 0. And as long as the bounds are the same, this will always be the area of the curve is 0. Next, the area from 0 to 5 of 7 times f of x. Well, we should make sure that we note that this is the same thing as the integral from 0 to 5 of f of x dx multiplied by the 7 once it's all done. So the understanding that this stuff right here in brackets is nothing more than this integral up here, we know that that area is 9. So if this area right here is 9, then 7 times that area is nothing more than that 63. Okay, so again, in terms of a constant being multiplied by the function, that constant can simply be pulled out of that function. Here, the integral from 0 to 2, now this one we're going to have to use this property right here. The integral from a to b is equal to a to c plus c to b. So knowing that I'm going from 0 to 2 is what I'm looking for. Sorry, it'd be, this is negative 1, this is 0, this is 5, and this value here is 2. Knowing that I'm going to go from 0 to 2 should imply that, well, if I'm going from 0 to 5, that distance is 9. So again, I'm going to make note of that. From 0 to 5 of f of x dx, that's equal to 9. But if I know also that the integral from x equals 2 to 5 of f of x dx is equal to 4, then if I were to take and look at the integral from 0 to 5 of f of x, that is the same thing as being equal to the integral from 0 to 2 of f of x plus, make sure I put that dx in there, plus the integral from 2 to 5 of f of x dx. But if I know what this value is here, and I know what this value is here, I could simply subtract this value over to solve for that integral. In other words, I know the area from here to here is 9, the area from here to here is 4. Well, that means that this space right here has to be 5. Otherwise, 5 plus 4 wouldn't be 9, and therefore this area from 0 to 5 wouldn't be 9. So I know that that area right there has to be 5 because, again, this total area 9 minus this space here 4 gives me 5 for this remaining spot right here. And I'm going to go ahead and put that in there into my little graph. Now we're going to go from -1 to 0. The exact same concept applies, but this is going to be a little bit trickier. So what I'm going to do with this one is I'm going to go ahead and write out the integrals that I'm working with. This is the same thing as being equal to the integral of x equals -1 to 5 of f of x dx. But I need to remove all of the area from x equals 0 to 5. Because again, I just want from -1 to 0. I want just that space. So if this is the total area, I need to remove from that the area that is not that I want. So I'm having from 0 to 5 in this space that I only want from -1 to 0. So if I remove that particular integral, I should be able to find the total area from -1 to 0. In this case, looking at my integrals, I have -1 to 5 is a value of 3, minus the integral from 0 to 5 is this value over here, 9, which means that the area under the curve for this object is -6. Now let's talk about that logically. If I were to, again, look at a curve, how am I supposed to get negative area? Well, negative area can happen with integrals if it's calculated, again, underneath the x-axis. So we could have a space here that is negative and a space here that is positive, but the thing is that this space here could be more negative than all of the other space from 0 to 5 over here. Okay? So that right there again is going to be -6. In this one right here, we're going to go from 0 to 2, which means that I'm going to go ahead and revert back to the concept of this rule. Now again, I'd have to go ahead and subtract 0, 5 minus 5 to 2 to get the range from 0 to 2. And then I'd take that value of 5, and I'm going to pull that 11 out of the integral so that I can understand that the integral from 0 to 2, that value right there is nothing more than 5. So this is 11 times 5, or 55. And then finally, this one right here, we're going from 5 to 2. So now remember, if I'm going to count values backwards, this is not from 2 to 5, this is from 5 to 2. So it's the same as this integral, but since I'm counting the area backwards, again, since I'm counting it from right to left instead of from left to right, this area ends up being a negative of that integral from x equals 2 to 5 f of x dx. Now keep note also that this also allows us to view this as simply a formula. Anytime that I want to switch these bounds that I don't like using the bounds that they're given, I can swap the order of the bounds and put a negative out front that integral, in which case I have -4 as that value. These are the properties of integrals. Again, all of these properties hold true for any continuous function that we choose to work with.